Alright, this video involves chemical nomenclature, and we will look at inorganic compound nomenclature. Another type is organic compound nomenclature. I used to teach that in Chem 1 in the past, but no more, and we're a little bit short on time this semester anyway, so we will leave that out. But no. Nomenclature of the inorganic compounds will be our discussion. So we will talk about covalent bonding a little bit. Start out with a little introduction here. And covalent bonding is illustrated as the Lewis structure in this first figure here. So these lines indicate covalent bonds. These are covalent single bonds, and that means that there are 2 electrons contained within each one of those bonds. So we say for covalent bonds that electrons that make up the bond are shared between 2 atoms, in this case the carbon and the hydrogen of the bond. For example, a CC represents a single bond, 2 electrons shared by 2 carbon atoms. Covalent bonds are formed between 2 nonmetals, so that's going to be the right-hand side of the periodic table, or a nonmetal and a hydrogen, like this case right here. So when we get a couple chapters down the road, we will be able to write Lewis structures for different molecules, covalently bonded molecules, and then we will look at the geometry. So this structure, the Lewis structure, doesn't tell anything about the fact that it's 3-dimensional and it's got a bond angles of 109.5, but the Vesper structure does. These bond angles are 109.5. So we'll get to the point where we can predict the Vesper structure for molecules as well. Okay, then we have ionic bonding, which is what we're going to focus on here. And this is different. It's an electrostatic interaction between charged ions. And ionic bonds are formed between a metal and a nonmetal. So that's the first thing. When you see a formula, you look at the elements and you say, okay, is it bond between 2 nonmetals? If so, then it's going to be a covalently bonded molecule, or a covalent bond, I should say. If it's between a metal and a nonmetal, then it will be ionic. So that's the first thing you want to look for here. So in the case of ionic, it's going to be metal and nonmetal. Now, some of this you already know, but let's just take a moment here and think about it. So in the case of sodium, the formation of the sodium ion, if you look in the periodic table, sodium is in position 11, so that means it's got 11 protons. It's going to have 11 neutrons if it's neutral, and I just picked some certain number of neutrons to make it a particular isotope. So this would be the 25 isotope, right? The sum of the protons and the neutrons. Anyway, we don't care about the neutrons. Now, what happens if an electron is removed? Then you're going to have 10 electrons. So in the case of the removal of the electron, now you've got 11 positive protons and 10 negative electrons. And in other words, you've got 1 more positive charge than negative, and that's why the ion has a positive charge. In the case of chlorine, it's in position 17 in the periodic table. 17 protons. If it's neutral, it's going to have 17 electrons. And then I just picked this isotope right here. This is going to be the 35 isotope because the sum of the number of protons and neutrons is 35. So in this case, the nonmetal, see the metal wants to lose an electron, the nonmetal will gain an electron. So actually the electron that's lost from sodium ends up being picked up by the chlorine. So then you have 18 electrons for chloride. So you've got 17 positive and 18 negative, and so you can see that there's 1 extra negative, and that's why the ion is negatively charged. All right, the next part here is this picture of the different elements. Sodium is a metal, and so you can see that it's just the atoms of sodium that are neutral, and they're just arranged in a very systematic way in a 3-dimensional array. All right, chlorine, on the other hand, it's diatomic, it's a nonmetal, and it's in the gas phase at room temperature. So here are the little chlorine molecules moving around in the gas phase. That's my dog there. And when you put them together, you have this reaction that takes place where the chlorine will separate, the Cl2 separates to form Cl, and then the electron gets transferred from the sodium to the chlorine. So you end up with positive sodium and negative chloride, and you have the ionic compound. But the picture that you see here is the ions that are arranged in a particular format, a particular form. And you can see the one face of what's referred to as the unit cell. Let's see if I can find another one here. This, 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 and this. That's on the side that's perpendicular to this one. And then you've got them on the top as well. So it's a particular type of arrangement. And, if we had more time, I would show you how you can actually calculate information about what's called the unit cell. Unit cell. And you can prove that the formula is 1-to-1 for the ions in this particular case. But we won't do that today. I'm going to skip that part. And so you see there's a big difference between covalent and ionic compounds. This is a plus-minus interaction in the solid phase. All right, then there are organic compounds and inorganic compounds. The difference between them: organic compounds contain carbon, and then inorganic compounds do not. So we use this term organic when we go to the grocery store, we go to Whole Foods or someplace, and we're buying organic food. That has a very different meaning than it does for organic chemistry. All it means in chemistry is that the compounds contain carbon. All right, so we're not going to really look at too many of the carbon compounds. We'll focus on the inorganic. Most inorganic compounds are ionic. Most organic compounds are covalent, but that's not a hard and fast rule for either one of those. Back here, whoops. All right, so the periodic table, this is a very interesting one. This is the periodic table of the ions. And so in the last video, we learned about representative elements and transition elements, if you remember. And let's see if I can blow this up a little bit. So the transition metals are here. Whoops. And then the post-transition metals are here. Okay. If it's a transition metal or a post-transition metal, then it has the possibility of having more than one charge. And if you look at this blow up a little bit more, the resolution's not so great, but you can see, for example, that cobalt can be 2+ or it can be 3+. It depends on what it's bonded to. Nickel can be 2+ or 3+, depending on what it's bonded to. Carbon is +2 and +1. Here's iron, 3+ and 2+. Chromium, 3+ and 2+. The pluses look like minuses, but they're not. Here's vanadium with 5 and 4. You can have 3 and 2 with vanadium as well. And then also you see that some of the transition metals do not have the possibility of forming more than one charge. And for example, zirconium just has one charge, which is +4. Zinc is +2. One thing some professors point out is that there's this relationship on this diagonal right here. Aluminum is +3, zinc is +2, and silver is +1. And they all just have one charge. Something you might remember. It's an interesting connection there. Now for the post-transition metals, you have the same situation that some of them can have more than one charge and some of them don't. And so this is a nice table. You could probably find a higher resolution version of this online. And then outside of the Transition metal, well actually down here on the lanthanides and actinides as well, you see that there's some of them, europium, americium, can have more than one charge as well. But then there are so those are transition metals, post-transition metals, but then there are these representative elements here and here, the rest of these guys, and you see that they only have one charge. So the metals are here, metals with only one charge. These metals can either have one or more than one charge. Okay, good to know. Stuff here. Okay. So it leads to a type 1 and a type 2 ionic compound. Just what I said to you, that whether it's got the ability to have more than one charge or not. So a type 1 ionic compound is going to be a representative metal. That's going to be these guys here, the ones with the A's, right? And some non-metal over here. So you get the plus and the minus interaction. And you can see some simple examples here. Sodium chloride. Another one is aluminum oxide, also called alumina. That's the common name. Potassium nitride and calcium phosphide. So you want to be able to figure out the formula and also the name. The naming, doesn't matter if you got 2s and 3s and 4s, whatever. If it's ionic type 1, you're going to name the positive ion, which is the cation. You're going to start to name the anion, stop, and then put IDE at the end. The IDE tells you that it's binary. Binary just means it's between two different elements, sodium and chlorine, aluminum and oxide, potassium and nitrogen, and so on. So if it's binary, you're going to see the IDE. And now if you want to figure out the formulas, you need to know a little bit more about the charges. So let me blow this up a little bit. And the charges are given here, but they're not given in most periodic tables. So you need to know that this is going to be +1. This will be +2. You can see that these three right here are +3, but boron is not, and certainly thallium is not. So you're going to have +3. And then for carbon, just kind of skip this one. You can make that 0. It's not always the case, especially for the ones lower down. But then to the other side, the charge for the anion is going to be, you can see it written here, but they're not always written. So it's -3, -2, -1, and then you have 0 here. That's a negative sign. So if you don't have this chart with all the charges given to you, you kind of need to know the numbers that I just wrote in red. And also note that if you take the 7 here in 7A, or remember this is group 17, so that's 7 plus 1 is 8, 6 plus 2 is 8, 5 plus 3 is 8. So you have 5 negative electrons around the central atom, and then you're going to add 3 more to make 8. That's the idea. On this side, you're going to add 3 more, add 2 more, add 1 more. On the other side, you're removing electrons, and you're going to remove 1 or 2 or 3, and that's why you have the metals losing and being +1, +2, +3. In any event, just remember those numbers, and you're good to go. Okay, so I'm not going to be giving you this chart, but since this is an online course, it certainly will be available to you. It's good, though, since you are science majors, to know this. We always require that students memorize the nomenclature and know how to put the atoms and molecules, the atoms or the ions together into molecules. It's very important that you know how to do it. So one of the drawbacks of the online course is that you got it sitting right in front of you, but nevertheless, in the long run, you need to know how to do this. So I would say put aside your notes, test yourself every which way you can. Make sure you know how to do this and you know the names of these elements and compounds. I didn't give you the Sorry, it was here, right? Yeah, okay. All right, so then if you want to figure out the formula of the compound formed between calcium and nitrogen, okay? You know that calcium's in group 2, so it's +2. Nitrogen is in group 5A or 15, therefore it wants 3 electrons, so it's -3. And so this is kind of small here. But you can write down calcium with a 2+, nitrogen with a 3-, and then overall you want your compound to be neutral. So if you have 3 + 2s, that's going to be -6, and 2 -3s, that's going to be -6. The sum of the two is 0 because the compound is neutral. Okay, so that's one way to think about it. The other thing is to realize that there's kind of a crisscross rule happening here. So you start out with, I'll write it down here. Let's go through it stepwise. Give myself a little space. So you can write down calcium and nitrogen. So the question is, what is the compound formed between calcium and nitrogen? You know you've got a metal calcium and a non-metal nitrogen, so you know it's going to be ionic. You know that it's binary because it's just 2 elements. You know the charge of calcium is +2 because it's in group 2. You know the charge on nitrogen is going to be -3 because it's in group 15 or 5A. So then you can just say, all right, well, 3, 2. And double check it, make sure it makes sense. So this is saying 3 calciums, each one with a +2, plus 2 nitrogens, each one -3, is equal to 0. Okay? And you can work backwards. You could say, for example, we'll do it with another one. We'll wait till we get to the transition metals for that. All right, so, hold on. All right, so then now for the type 2, I gave you all the information already. You're going to be looking at transition metals or the post-transition metals. I'm not going to ask you anything about the lanthanides and the actinides except for their position in the periodic table. All right, so if it's type 2, then you can have compounds, for example, like Fe. You could have FeCl2 or FeCl3. So why did I do that? Because iron is going to be +3 in this one. Chlorine will be -1. This is going to be +2 and -1. So crisscross rule would come up with those formulas. The systematic name is going to be iron with a Roman numeral. 3 in this case. That's the charge on the iron, and then Roman numeral 2 because that's the charge right there. I actually feel like I need to make some space and write this out. So you have Fe2+. We know that chlorine is -1. Crisscross rule is going to give us a 2 and a 1 there. You don't write the 1 in. This is all your busy work. You want to, in the end, write down this, FeCl2. And then the question is, what is the name of it? So the name of it is, if it's a type 2 compound, you got to put the charge in and you got to use Roman numerals for it. So it would be iron 2, and you don't put in parentheses, it's just iron Roman numeral 2. You start to name you start to name the anion, you stop and you put an IDE because it's binary. Okay, now instead, if you have iron 3 with chlorine, which is -1, then you're going to have FeCl3. What is the name of that compound? So that one will be iron 3 chlor, oops, I need to put an L there, chloride. So there's a difference then between iron 2 chloride and iron 3 chloride. Now the common names are also given, ferric and ferrous. So you could say that the name is ferrous, F-E-R-R-O-U-S, chloride, and ferric, chloride, and ferrous. The OUS tells you that this is the one with the lesser charge. The IC tells you that this is the one with the greater charge. So you got +2 versus +3. OUS and IC tells you which one is smaller and which one is larger. It doesn't give you an exact number. You can have, for example, cupric and cuprous. And cupric is going to be, the IC is associated with the larger number, the OUS, the smaller number, but notice that the numbers are different. IC does not mean 2. It just means the larger one. So am I going to ask you for these? No, I'm not, but they're very interesting to look at. Ferric and ferrous, cobaltic, cobaltus, cupric and cuprous. This one you hear sometimes. Stannic and stannous. Stannous fluoride is in your toothpaste. Plumbic and plumbus. It's also interesting because the symbol for lead is Pb, right? So it comes from the Latin. And then mercury, you have mercuric and mercurous. This one you hear oftentimes as well. So I'm just pointing them out because they are the common names, and oftentimes you run into them in your travels. Different molecules, different compounds, situations. All right, so that's type 2. Type 2 are metals, transition metals and such that can have more than one charge. And again, we can look at the crisscross relationship. We have titanium and nitrogen, and we are given that this is the +4. The +4, well, we're given to it up here. Start with titanium 4 and nitrogen 3. Put them together, and you have the crisscross relationship, 3 and 3, 4 and 4. So you have 3 times +4 plus 4 times -3, and that's equal to 0. So that means that's consistent with it being a neutral compound. What is the name of the compound? Is it titanium nitride or is it titanium 4 nitride? The answer is it's titanium 4 nitride because titanium can have more than one charge. So titanium 4 nitride. And if you're not sure about the Roman numerals, you can look them up. Titanium 4 nitride. All right. So here's a little bit more on the same subject, and this is what I just went over with you, iron 2 and iron 3. These are the names of the compounds. Lead can be either 2 or 4. So you can make, because oxygen is in group 6A or 16, this is going to be -2. So you got a +2 and a -2, makes lead 2 oxide. For the compound, actually let's work backwards on this one here. So if you had lead oxide, that's not the correct name, but I just said it. You could figure that oxygen is always going to be -2. There are some exceptions to that, but for the moment anyway, we'll say that oxygen is behaving normally and it has a -2 charge. All right, so that's going to give us 1 here. You could say that's X, right? So you could say 1 times X plus 2 times -2 is 0 because it's neutral. So this is going to make X equal to +4. Now you can do that in your head when you get more comfortable with it. But does it make sense? So you have lead 4 oxide -2 plus 4 and 1 there. And so you get, and so the name of the compound is going to be then lead 4 oxide. which is this one right here. All right, so there's just a couple more examples for that. Now we want to switch to binary covalent. We looked at binary ionic type 1, binary ionic type 2, and this one now is going to be binary covalent. And this is going to be between two nonmetals. So before we were looking at metal versus nonmetal, now we're looking at the combination of two nonmetals. So how do you know whether if it's ionic or covalent? Exactly that way. If it's two nonmetals, then it's going to be covalent. So here's some examples of nonmetals that are combining. You have nitrogen and oxygen, carbon and oxygen, sulfur and oxygen, phosphorus and iodine. And for this, since it's not ionic, you work with something called oxidation numbers instead. We're going to study them a little bit further down the road. But for the moment, we'll just look at the formulas and come up with the names for them, okay? So the notation is different here. The naming is different. You have, for the number of each of the atoms, each of the elements, you're going to use the notation here. Mono means 1, di is 2, tri is 3, tetra is 4, 5, 6, 7, 8, octa is 8, nona, and deca. We won't bother going higher than deca. So sometimes you don't have the A there. Sometimes it's just like dec, known, but sometimes you do have the A there. And so I'll show you a couple of exceptions as we go ahead here. So you still have the IDE, and that means that it's binary. It's just between two elements. You have that. So instead of, if it were ionic, we would call this nitrogen oxide or nitrogen 5 oxide, but it's not. It's covalent. So it's covalent. If you have N2O5, what is the name of the compound? So it'll be dinitrogen because you have two nitrogens, and pentoxide, dinitrogen pentoxide. So here we have it, dinitrogen. You write out the entire name of the element, and instead of saying penta, because there's an oxygen in the word in the part oxide, you're going to drop it. So in other words, you could say dinitrogen. Then you want to say penta, P-E-N-T, but you drop the A because the oxide starts with a vowel. You only want to have one vowel there, and the IDE tells you that it's binary. So you have a difference here between carbon monoxide and carbon dioxide. So monoxide means that there's one oxygen. Dioxide means that there's two oxygens. Now, notice that mono on the top here means 1. So technically, we could say, since you have one carbon and one oxygen, technically you could say monocarbon monoxide, right? But the convention is, if it's mono on the first element, you leave it out. So it's carbon monoxide. The mono here is assumed. And it would be the same with carbon dioxide. It would be monocarbon dioxide. Here you can have both two vowels present here, but not with the A and the O. But the convention, again, since it's mono on the first element, you leave it out, carbon dioxide. Same with sulfur dioxide as well. Then last one would be diphosphorous tetroxide. All right, now we look at binary acids. This is the fourth type of compound we're looking at. These can be covalently bonded or exist in the ionic state depending on what the phase is. But binary acids are going to involve a hydrogen and then a non-metal. So this part over here. And if you look at this table, you can see that the names are different depending on whether if it's in aqueous phase or gas phase. So it's the same HF compound, but the names are different because of the phase. Hydrofluoric acid, hydrochloric acid, hydrobromic acid. Down here, hydrosulfuric acid, hydroselenic acid. In the gas phase, it's completely different. Hydrogen fluoride, hydrogen chloride, hydrogen bromide, hydrogen, iodide, sulfide, and selenide. So what is the difference here? And in the gas phase, look at HCl, you have a covalently bonded molecule. That's why it is called hydrogen chloride. In the aqueous phase, this bond breaks, and then each one, it becomes ionic. You get the H plus and the Cl minus. So both of the electrons here end up on the chlorine. So that's how you get -1. One that originally belonged to chlorine, and then the one from hydrogen comes over here. So, and then water molecules are solvated all around these ions. So you get plus H plus. AQ means that there are water molecules surrounding the H plus, and then you get chloride. Same thing, AQ, aqueous, means water molecules are surrounding. So when it's put in water, it's actually more stable for it to break up into the ionic form and to be solvated by water than it is to remain as a covalent molecule, and that's why it happens. So it's a very different situation in the aqueous phase, and the name reflects that. Hydrochloric acid is the name for the aqueous phase. All right, next are the oxyacids, and they are a study in themselves, but listed here are the polyatomic ions that are formed when they go into water. Okay, so let's just take it one step at a time here. So let's see, let's look at the first column. Oxy acid, what does that mean? It means you've got a hydrogen. The hydrogen on the left tells you that it's an acid. Then you have a non-metal, carbon, phosphorus, sulfur, nitrogen, and then one of the halogens. And then there are some oxygens connected to it as well. And you can have more than one oxygen forming different compounds. In this case, you got 4 different types. So the oxy acid is a hydrogen, a non-metal, and some oxygen. And the names reflect the non-metal, so carbon, phosphorus, sulfur, nitrogen, and chlorine. And then you have this situation where, for example, here you have a difference between IC and OUS again. The IC in phosphoric acid is telling you that between these two types of phosphorus oxyacids, one has 4 oxygens, the other one's got 3. The 4 is greater, the 3 is smaller. So with sulfur, you also get a 4 and 3 combination, and you see the IC and the OUS. With nitrogen, it's different. You get a 3 or 2 combination, but you have the greater and the lesser, the larger or the smaller number of oxygens. So that's the trend. Now, with the halogens, you can have fluorine, chlorine, bromine, or iodine, and there are 4 possible ones. The ones that I have in blue here behave similarly. There's an IC and an OUS, so the 3 and the 2. But then you put per in front of it, perchloric, to indicate the maximum number of oxygens possible. And here you have a hypo in front of so this is a per in front of chloric acid, and this is a hypo in front of chlorous acid. And hypo means it's the least number of oxygens that are possible to be bound by it. Okay, so you got to memorize these, even though on a test you got them sitting right in front of you. You got to memorize them anyway. You need to know these if you're going to be able to talk chemistry and science with other professionals that you will undoubtedly interact with later in life. All right, now what happens when you put them in water? So you're going to get dissociation here. The hydrogens are going to break off, and in this case 2 of them will be given up, and then you have this part left over, carbonate. The hydrogens leave in the form of H+, and so you get the electrons end up sitting on the CO3 part, so it becomes 2 minus charge. Same thing here, phosphate remains PO4 3 minus when the 3 H pluses go into solution. So it breaks up into, let's see here. So if you have H3PO4, phosphorus acid, you put that in water. I'll put water over the arrow here. Then it'll break up into 3 H pluses, aqueous, and then the 3 electrons stay behind and you get phosphate, and that'll be aqueous as well. So that's the process. Phosphate is the name of the polyatomic ion formed from the dissociation of phosphoric acid. I'm sorry, I said phosphorus, but I meant phosphoric. So it's phosphoric acid and phosphate. They're being formed. All right, now in the case of hypochlorous acid here, down at the bottom, we have something that you might want to know about. You'll see it sometime on a test or so. So you have HClO, that's hypochlorous acid. When you put it in water, it's going to break up into H+, aqueous, plus the polyatomic ion hypochlorite, also aqueous. And sometimes it is written as ClO, sometimes it's written as OCl minus, hypochlorite, either this form or this form. This is what you would predict by just kind of breaking the covalent bond right there. But this is the one that's typically designated and referred to for hypochlorite. And there's reasons for it. We'll actually see later on why sometimes we write it that way as OCl minus. Don't have to worry about it right now, but you might see it in the nomenclature test. So if you had something like, so the polyatomic ions can form salts, right? So that's going to be a cation and an anion, an ionic compound. So in other words, not only do you have binary type 1 ionic compounds. Okay, let's consider this for a moment here. So if you have binary type 1 ionic, you could have sodium, I don't know, iodide, something like that. Okay, so sodium iodide, that's simple. And I told you that this is formed between a metal and a non-metal. But in this case, where you have these polyatomic ions that are formed, let's look at this table again. So these are the polyatomic ions. Why did that shrink like that? This column is the polyatomic ions that are formed from these oxy acids. And you could think of these as, you know, like here's nitrate, right? It can form an ionic compound with, what was the one I had right there? With sodium. So you can have, what that line is there. Oh, something funny happened in here. Okay. So, oh, something with the camera. I see. Okay, I didn't realize that happened. Let me go back. I'll go over to the side. Okay, so you could have a compound between, you know, sodium, what was the one I said? Sodium and nitrate, was that it? So you can have sodium nitrate here. And it's similar because you got a sodium plus. This is a type 1 metal, but it's not with a non-metal. Instead, it's with a polyatomic ion that has a negative charge of 1. So the naming is really similar. It's going to be sodium. You don't put the charge in. You could if it were a type 2 metal instead of a type 1. But you just say sodium here, and then you just write down the name of the polyatomic ion, which is nitrate. All right, so sodium can be with a nonmetal, or it could be with a polyatomic ion. That was the point of this digression here. We probably want to take well, actually we'll get to it a little bit. Yeah. Okay. All right. So then so we want to look at some more of these polyatomic ions that were not given on the last slide. Here's a list. You've got some positive polyatomic ions, ammonium and hydronium, and those are the only two positive ones. And then you have negatives. You have bisulfate, bicarbonate, permanganate, hydroxide, cyanide, acetate, chromate, dichromate, peroxide, superoxide, oxide. Now I mentioned that oxygen normally is -2. Here are the two less common forms of oxygen. And you can have, let's see here, if you have sodium oxide, that's going to be oxygen behaving normally. Since oxygen is normally -2, and sodium is always +1, that'll give us a formula of sodium 2, oxygen 1. And we would write that as Na2O, sodium oxide. This one right here is a superoxide, and notice that it's got a negative charge. So you could have something like sodium and superoxide, something like that. We know that the superoxide ion is -1. So in other words, you got two oxygens together. In total, the charge is -1, which means each oxygen in the superoxide is actually -1/2, which is okay. You can have fractional values. So the whole thing right here is -1, and sodium will be +1 with that. So then you would write it as NaO2 as opposed to Na2O, right? And this would be sodium superoxide. Okay, and then the third one here is peroxide, and this one is an O2 again, but this time it's got a 2-. So if you wanted to do sodium peroxide, very explosive by the way, then you would write sodium, and the peroxide is O2. We know that it's got a charge of -2. There's one, sodium's always +1, so that would give us a, let's see, what would this be? Sodium 2 there. So it would be sodium 2, O2. Let's see if I got that right. Yeah. So that's sodium peroxide, Na2O2. All right, will I ask you about that? Probably on a test. You got to know all these polyatomic ions by name. You need to know the name, the formula, and the charge on each one of these, and the ones in the previous slides as well. Make up some flashcards for yourself. In the past, I have done flashcards for you on Quizlet, and I find that students don't really pay attention to them. It's better for you to make up your own flashcards for this. Okay, and then we have thiosulfate here, S2O3. This is one that you work with in the lab quite often, and oxalate's an important one as well. All right, you gotta learn them. Just go forward here. Next is partial neutralization, and this is for sodium hydrogen sulfate and sodium hydrogen carbonate. I will give you the example for sodium bicarbonate, NaHCO3. So let me do that. NaHCO3. Actually, there are 3 forms of the carbon oxygen CO3 species. The first one is going to be H2CO3. Then you can have one of the hydrogens removed. So one of these hydrogens comes off as H+, and you end up, I'm going to write the ion here on the side. It makes it a little bit easier to see this. So you have H2CO3. One of those hydrogens is removed, and so you have HCO3-. And then it's possible to remove the next hydrogen here. And so the third in the series would be CO3 2-. Now, since these are ions here and here, then they would want to hook up with some positive cation like sodium. So you get sodium +1, hydrogen carbonate. And then the other one would be, for the carbonate, you'd have Na2CO3. All right, so I gave you a lot of information there. Go over that a couple of times. And the names on the right here are carbonic acid, hydrogen carbonate, and carbonate. Okay, so hydrogen carbonate could lose a proton or a hydrogen and form carbonate, or it can gain a hydrogen and form carbonic acid. So it could go either way depending on whether it's an acid or base solution. This is the same here, carbonic acid. The name of this one would be sodium, hydrogen, carbonate. And the name of this one would be sodium carbonate. All right, so in other words, hydrogen carbonate is the name of the anion and carbonate there. Okay. So we're almost at the end. A couple more slides to go on nomenclature. And let's just look at a random mix here and name the various compounds. Catch my breath here for a second. So we could recognize PCl5 is a combination between 2 elements, both are nonmetal. So phosphorus is a nonmetal, chlorine's a nonmetal. So we might say monophosphorus pentachloride, but we're going to leave off the mono. So this one will be phosphorus. Penta, you can leave the A. And chlor, CHLOR, you stop and you put IDE there to indicate it's a binary compound. Similarly, NF3 would be nitrogen, tri, FLUO, sorry, whoops, that one. FLUORIDE, nitrogen trifluoride. And next one would be silver sulfate. Now you have to go to the periodic table. Silver is a transition metal, but it happens to be one of them that's just got one charge, and that one charge is +1. So sulfate, the ion sulfate is going to be -2. So you could think of it this way. Sulfate is -2. Silver is +1. So there's the crisscross rule, 2, and so the sulfate you can think of as being 1. I better write that bigger. What do you think there? Let's do that again. All right, so silver and sulfate. Sulfate, the entire thing is -2. Silver is +1. You can use the crisscross rule, right? And you have a 2 here and a 1 here. You don't put parentheses on the sulfate because it's just one of them, but we'll look at another example of that in a minute. So then this translates as silver 2 sulfate, and you don't have to put Roman numeral 2, it's got 2 silvers and a sulfate. The name of the compound will be silver 1 sulfate, but because it's only got one charge, you just gotta call it silver sulfate. All right, so this one is silver sulfate. Oops. All right, the next one is going to be, it's between mercury and carbonate. CO3 is, now I don't want to hear you say or see you write monocarbon trioxide. You got to know that carbonate is a polyatomic ion with a -2 charge. So if you know that carbonate has a -2 charge, then you know that mercury has to be a +2 charge. So let's do that in detail here. You know that carbonate, because you've memorized it, is -2. Therefore, this mercury has to be a +2 because it's 1 to 1 there, right? So the name of this, mercury can be either +2 or +1. So the name of this one will be mercury 2 carbonate. All right, the next one will be copper can be either +2 or +1. Since each chloride is -1, then this is going to be copper 2 chloride because you only have one copper there. So this would be copper 2 chloride. The next one is with zinc and a nitrate. You have memorized that nitrate, each nitrate here is -1. You know that, and there's 2 of them. So that makes the right-hand side -2. You got 1 zinc, so it's going to make zinc +2. So with that one, you're already given that you got 2 nitrates there. Trying to think of a way to simplify this. You have memorized that nitrate is -1, and the fact that you got 2 of them. So let's see here. So if you had zinc and you've got nitrate here, each one is -1, but you have 2 of them. So you've got 1 zinc in the formula, you can call that X. Maybe that'll help. So 1 times X plus 2 times -1, it's going to be 0 because it's neutral. And this is X will be equal to +2. So this would be zinc 2 nitrate, but zinc is a transition metal. It happens to be one that only has 1 charge, so you don't have to call it zinc 2 nitrate. You can just call it zinc nitrate. That's Tr right there. All right, hydrogen sulfate is a partially neutralized sulfuric acid. So remember that's going to be hydrogen sulfate or bisulfate. Each one of those you have memorized to be -1. You've got 2 of those, so that's going to give you calcium 2 hydrogen sulfate. But calcium is a type 1 metal here, so you don't need to put the charge in. So this one will be, let's see if I can blow this up a little bit. This one will be, let's get a different color here. Calcium. You don't have to put the 2 in there, +2, but it is +2. That is +2 right there. And then so it'll be calcium, hydrogen, sulfate. These are a little bit complicated, but I know you can do it. Then you have vanadium 3 hydroxide. Vanadium's a transition metal that can have more than one charge. So vanadium 3 hydroxide. Hydroxide is a polyatomic ion. Behaves like a non-metal, forming the ionic compound. And then the last one's tricky, HBrO2. And with HBrO2, remember the series. So you have, we're looking for HBrO2, but in fact, there's this series, right? So HBrO4, HBrO3, HBrO2, and HBrO. So the examples that I showed you had chlorine instead of bromine, but otherwise it's the same naming. So the first one would be perbromic acid. Next one would be bromic acid. Next one is Bromis acid, and then perbromis acid. So this is the one you're looking for. The name of HBrO2 is Bromis acid. Most people don't get that unless they recognize that it's a compound formed between hydrogen, nonmetal, and oxygen. So it's one of those Oxy Acids. And if we pulled out the hydrogen by putting this compound in water, you'd have BrO2 minus, and that's going to be bromite. Bromite. I don't know if you can see that there. All right, and then I think just a couple more. This one, write the formulas associated with the names. So this one would be, you got copper here and sulfate. You know that sulfate is -2, so this is going to be +2. So this would be copper 2 sulfate. You want to put the Roman numeral in there because it's a transition metal. Next one is going to be calcium and chromate. So you have, there's a couple more I got here I want to show you as well. So calcium chromate is going to be, this one's copper, this one's calcium, and chromate is CrO4. CrO4 with a 2 minus, calcium's got a 2 plus, and so that will be the formula. The next one is potassium permanganate. Permanganate's a pretty popular one in the laboratory. The permanganate ion is -1. It's that gorgeous purple color associated with that ion. And permanganate's going to be -1 there. So it'll hook up with a potassium, which is going to be +1 because potassium's in group 1. So the answer is going to be K. So that negative charge for permanganate is on the entire polyatomic ion. Same thing here for the chromate. It's -2 on the entire polyatomic ion. Same thing here. So this will be KMnO4, potassium permanganate. That's a good one. I've been known to ask that one on tests. Nitrous acid versus nitric acid. Nitric acid is HNO3. Nitrous acid is going to be HNO2. Sodium hypochlorite. Remember the hypochlorite, you can write sodium OCl or you could write sodium ClO. This is the one, even though it's backwards to the regular convention, that's the one that most people write and use. All right, and maybe we have one more, maybe we don't. Yep, we do. Okay, so the last slide here. Write the formulas for compounds formed between iron 2 and phosphate, iron 3 and phosphate, iron 2 and phosphite, iron 3 and phosphite. So just an exercise in crazy right here. So you do your busy work first. You got iron 2, phosphate is PO4 3-. So crisscross rule here. It's going to give you a 3 here, and this goes in parentheses. Polyatomic ion goes in parentheses. You get 2 of those. Okay, that's just using the crisscross rule. So then the answer would be Fe3, PO4. Put the parentheses in, and you got 2 there. So the name of the compound here is iron 2 phosphate. All right, the next one, you got iron 3, phosphate 3- on the whole thing. So it's 1-to-1. Iron 3 phosphate would be the name. Then you got iron 2+ here with phosphite. Phosphate, it's PO3. And the 3- is on the whole thing. So you're going to have 3 and 2 there. That's your busy work. In the end, you don't put the charges above it. You just say iron 3 phosphite. And actually, that's iron 2 phosphite, as you can see. And that should be a little space in there. Just parentheses. Then the last one would be iron 3 and phosphite, PO3 3-. So that's 1-to-1. So your answer here is going to be FePO3. All right, if you're systematic about it, you can figure it out. What if I gave you these? Could you work backwards and give me the names, right? So you know that the first one is going to be iron 2 by the crisscross rule, right? So iron 2 phosphate. Here it's going to be +3. Here it's going to be +2. Here it's going to be +3. So the names will contain that iron 3 phosphite, iron 2 phosphite, and so on. All right, well, that was quite a bit of work on the nomenclature. This takes a lot of thinking. Let me show you one more thing here quickly. What you had, for example, N3-, NO2-, NO3-, N2O3, N2O5, that's a 5 there, NO2, just to show you how many compounds are formed with nitrogen. It's truly amazing. NO3 and N2O4. What are the names? The first one is going to be nitride. That would be paired up with some kind of a cation like sodium. So it'd be sodium nit. You'd start to name nitrogen, and then you'd say IDE. So this is going to be nitride, IDE. The next one is nitrite. This is why I want you to be careful. The next one is nitrate, ATE, greater and lesser number of oxygens, right? This next one is this is between 2 nonmetals, so it's dinitrogen trioxide. Then you have dinitrogen pentoxide. You leave the A off the penta. Then you have mono, but you're going to leave that out, so it would just be nitrogen dioxide. And then NO3, compare these two, they're different, right? The second one here is nitrogen trioxide. And then the last one is going to be dinitrogen tetroxide.